Thanks for the opportunity to give a talk at this very nice workshop. So I will today speak about determinant weights and Rankin's trick. So first I want to apologize because I realized this morning that some of my notation might be a bit off. So please stop me whenever my notation confuses you, and hopefully things will still be fine. Okay, so let me start by giving you some of my notation. By the way, do you see my mouse when I move this? You see this? Great. So in this talk, K will be a finite field with some fixed algebraic closure K bar. And I will also fix an isomorphism tau between the algebraic closure of QL, the L-adic numbers, where L is not equal to P, and the complex numbers. And as you know, this is just convenience and exists by axiom of choice. I think Deline writes in Weil 2 that he doesn't believe in the axiom of choice and thus doesn't believe in this isomorphism, but it's not really important because you can show that all numbers that appear will be algebraic. All right, so let us recall the following key theorem from Sev's talk. This will be very important for us today. So the theorem is the following. So let x0 over k be a normal and geometrically irreducible scheme. Now we have let A be a geometric point of x0. Then the theorem says that whenever we have a character growing from the Weil group of x0 and into QL bar and the units here, where L is not equal to P, then this character will restrict to a finite order character on the geometric fundamental group. And this implies that you can write the character as a product of two characters, chi1 and chi2, and where chi1 will be of finite order and chi2 will factor through the Weil group of the base field. So this is a foundation for everything we will do today, more or less. So as I think Sev said yesterday, is that we also have the following very important corollary, is that any list sheaf G0 on X0 rank 1 will be tau pure. Why? Well, this follows from the above theorem, because by monodromy, you have that G0 will be given by some character from the Weil group into QL bar and the units there. And further, by what we said above, you can then write the character as a product of two different characters. And this implies that the sheaf, the list sheaf you have, is isomorphic to a product of two other, a tensor product of two other list sheaves, which I call F and H. And now, since we know that chi1 is of finite order, this implies that F has weights that are roots of unity, because you have that F tensor n is just QL bar. And you know that H is pulled back from spec K. This is because the character factors through this Weil group of the base field.
Sorry, you mean the eigenvalues are roots of unity, I guess.
Yes, precisely, not the weights. The eigenvalues are roots of unity. Thanks. Right. Yes. And you see, because H is pulled back from spec K, the point, it doesn't matter what point you take the Frobenius and it will still be the same. Right. So this is the important corollary for today. So we will use this now to define some new notion of weights. So why would we want this then? Well, there's, I will not say a problem with the current notion of weight, but it's sort of like some minor inconvenience with our current definition of maximal weight, is that in some sense this is not terribly easy to calculate at the moment, because we're taking some supremum of the weights calculated at every stalk of our scheme. So it would be easier somehow if we could just have some notion of a weight, which I could just, you can just give me any point of the scheme. And then I can just look at the corresponding representation I have at this point. And if I could somehow use some linear algebra to just get some notion of weight from this point, this would be somehow preferable because it would be less data, less things to go through. So this is what we'll now try to do. We will try to define some new notion of weight, which should be able to be calculable from just one point. And we also just want, so to say, we want this also to be meaningful in some sense. I mean, I can just define the weight to be 0 at every point, but it will not be meaningful. So we want this to also carry some meaning. So here's a desiderata for some new notion of weight, what we would want from this new notion of weight that I'm speaking of. So first of all, as you said, I want this notion of weight to be calculable by just looking at one point. This is the first thing you want. And then second, and this is maybe most important, is that this new notion of a weight, it should be tightly linked with our previous notion of weights. So we should be able to somehow, yeah, there should be a tight relation between the two, which may just not be anything we can come up with. And third, and this is also important, is that we want this new notion of weight to behave well with tensor products and exterior products. And the reason we want this is the following, because when we want to prove inequalities, we often want to be able to use some tensor power trick. And the tensor power trick is like, say that we want to show an inequality as x is less than or equal to y, for x and y some non-negative quantities. But say that initially we can only prove that x is less than or equal to c times I, for c some constant greater than 1. Well, this is then shame, but say that we can prove instead that x to the power of m is less than or equal to c times y to the power of m for all m. Then we can, of course, just take mth roots and let m go to infinity to get x less than or equal to y. So some version of this tensor power trick often comes up when you want to prove certain inequalities in this world. So this is why it's important to have that this notion of weight should behave well with tensor and exterior products. And lastly, we want this to behave well with respect to maps between schemes. And I will not really go into exactly what kind of maps we want it to behave well to. So 4 things. Our new notion of weights should be calculable by just looking at one point. It should be tightly linked with.
By calculable by just one point, you mean like independent of the point you choose, or that there is a specific point such that it is calculable from it?
I want this to be, you should be able to calculate for any point you give me. So I mean, it should be independent and it should be able to calculate from one point.
Okay.
So, and I also want to be linked with previous notion of weights, and it should behave well with tensors and exterior products, and should behave well with respect to maps between schemes. So determinant weights will fulfill the above list of desiderata. So let me just try to motivate how to think of this. So I will now give a very stupid definition of a determinant weight, which is not the correct thing, but it's close to the correct thing. And then we will see what the correct thing is. So the following is a stupid and obvious thought of how we could fulfill one. Pops to mind. If we just consider the theorem I looked at corollary here, so that whenever we have a list sheaf G0 and X0 rank 1, it is tau pure. Okay. So then say that I have a list sheaf on X0. How can I go about to create a list sheaf of rank 1? Well, I can take the top exterior power. That is, I can take as determinant. Let us try to do this then. So now this stupid new notion of weight is the following. So given G0 over X0 that's lists, take the top exterior power, and this is now rank 1. And what we have just seen, that is tau pure, and we can just calculate this as 1 point. So this surely fulfills 1 then. But it's not really a good fit for 2 of our desiderata. because we will lose a lot. Of course, we will lose a lot of information when we just take the determinant. Here's just one example. So if we let x0 be the projected line, now let g0 be the list sheaf of rank 2, as given by the matrix alpha alpha inverse, where alpha is an element in QL bar I want. Then this list sheaf here will be pulled back from spec K because the geometric fundamental group of the projected line is just trivial. And now clearly when I say this new weight that I've spoken about, which is just taking the top x0 power and the weight of that, it will be 0 because the determinant of this is 1. So you see, we have of course no hope of recovering the eigenvalues from determinants. So clearly this was a stupid thing to do. Now, can we be a bit less stupid? And by looking at this example, we see there is some way we can actually recover the eigenvalues from this thing. Above here, we have a filtration of our sheaf G0. First, we have 0, which is defined as here G2 0. It's sub object of G1 0 and G0 0. And here we have that each quotient is irreducible. And you know that here we can see that the eigenvalues can be recovered from the determinant of each irreducible constituent. That is, when I have this Jordan-Holder series, I can look at the quotients. And if I take the determinant of each of those, I can recover the eigenvalues. So in this particular example, we see that if we just tweak this idea a bit, we can recover the eigenvalues. For more general schemes, x0 over k, the situation is of course more complicated, but we will try to mimic this idea to define the general determinant weights. So here's the official definition of determinant weights. So let x0 be geometrically connected and normal over k, and let g0 be a list sheaf on x0. So given a composition series of G0 with this quotient Fi, which is defined as Gi mod Gi minus 1 of rank, when we say that this quotient is rank Ri, you can then define the tau determinant weights of G0 as 1 over Ri, where Ri is the rank of this guy here, and then the tau weight of this top x0 power. And the reason we divide by Ri is we want the determinant weights of a pure sheaf to coincide with ordinary weights. So is this definition clear?
Do you demand anything about the composition series?
I want the quotients to be irreducible, but otherwise no.
Okay.
So, anyone else have questions about the definition? Because it's important that we.
Is it obvious that yes, it is obvious. Just like I wasn't sure like why you have the composition series. Why are you?
Oh right, I see what you're saying. So
opinion, but
yeah,
vector spaces. Yeah.
Right. Yes. So I mean, yeah. So I think you can look at the representation, then you can get this. If you look at the corresponding representation, you can get this composition series.
Yeah, I have a question, Magnus.
Yes.
So if we had an example of an irreducible sheaf which is not pure, then
yes,
this would mean that this definition forgets some information in this example.
Yes.
Okay.
So I will come back to that point later on, actually. Thanks for bringing it up. So let me just remark shortly that this is independent of composition series because the isomorphism clauses of the Fi does not depend on the filtration. So I just want to ask one last time. Is there any further questions on this definition of determinant weights or anything previous? I know also to ask about that.
It is independent of the composition series, right?
Yes. So what was the question, Leor?
I just want to make sure that the definition is independent of the composition series that you choose, like because the factors are independent.
Right, but I mean, this is because the isomorphism clause of the Fi appearing is independent on the filtration.
Yes.
So this means that all these guys appearing here will not depend on what filtration I choose.
Right.
Yes. So let us now show that this determinant weights satisfy our listed desiderata from before. So then the 1, which was the point that it could be calculable from 1 point, is now obvious. And the reason why it's obvious is because we know that all these quotients here are pure. So they can be so the weights can be calculated at 1 point. And 3 and 4, so recall that 3 was the thing that we wanted it to behave well with tensor products and exterior products. And 4 was that we wanted this notion of weight to behave well with respect to maps from I0 to X0, or with respect to maps between schemes. So this is not as trivial, but it's not that hard to establish once we recall the following, which was proven yesterday by Seb. So I think this is part of Grothendieck monodromy theorem. So the theorem is as follows. So let G0 be a geometrically semi-simple List sheaf on a geometrically connected normal scheme X0 over K. Then if we let Z be the center of GQL bar, where G is the arithmetic monodromy group, then the natural map from the center into the V group of the base field has finite kernel and co-kernel.
Can you remind which one is the arithmetic monodromy group?
Sure. So the geometric monodromy group is the Zariski closure of the representation on the geometric fundamental group, and the arithmetic monodromy group is the semi-product with the Weil group. So where you have that, so you recall that the Weil group is isomorphic to Z. So there you can form this group scheme by having Z act on the monodromy, geometric monodromy. So is that clear?
Yeah, kind of.
So it will not be that important for us, the precise definition. I mean, this will be what we'll need.
Magnus?
Yes?
So we're not assuming that G0 is semi-simple, right?
No, not in the definition of the determinant weights. But you see, we will use this. It will be
just for the quotient.
Yes, we will use
looking
this.
on the associated graded. So
yes, we'll look at the semi-simplification of our list sheaf.
Yeah, thanks.
Yeah. Thanks.
Magnus, another question.
Yeah.
So in the definition of determinant weights, we asked that they are geometrically semi-simple.
No, that's not something we want. We don't. Not something we ask.
Okay, if they are
we only wanted. We only. Yeah, see what you say. No,
geometrically irreducible, I meant.
No, I think that's not what we're. I think we just take any list sheaf. I think that's.
I mean, the composition series has quotients which are irreducible or geometrically irreducible. That's the question.
Oh, I see what you're saying. I think we just take irreducible.
Okay.
That's my impression. Right. So here's a corollary from this theorem, which I think Seb mentioned yesterday. So let G0 and X0 be as above. And so G0 is geometrically semi-simple, and X0 is some geometrically like normal scheme. Let's choose some Z in the center such that the degree under this map here is M, and M is not equal to 0. And let us suppose now that alpha 1 up to alpha r are the eigenvalues of Z acting on this G0 X, where X is some geometric point. This is the stalk of our sheaf. I suppose that the values of the absolute value of tau alpha I is equal to Q M to BI. And here Q is the size of our residue field. then the beta I are the determined weights of D0. So this tells us that when we have some element here in the center, we can calculate the determinant weights by looking at the eigenvalues of this, of Z. Because you see that what it says is that the absolute value of tau alpha I is equal to Q MBI. So is the statement of this corollary clear to everyone? Or should I try to clarify it?
It's basically the remark that Zev said yesterday, right? That you can compute the weights from the center if you know the degree of an element.
Precisely, it's precisely that remark. So I'll go to the proof, but stop me if you don't understand the statement of the corollary. So you see that the proof is as follows. On an irreducible constituent or irreducible component, Z here will act by multiplication by scalar from Schur's lemma. Now, on the other hand, you see that we can easily reduce to the situation when G0 is irreducible. Then you have that the determinant weight of G0 will be isomorphic to a product of F and H. And F here will be something where the eigenvalues of the Frobenius are just roots of unity. And here this H here is pulled back from the subcharacter of the Weil group. And you can, as I said, that the determinant of D0 will be given by some character chi is a product of chi1 and chi2. And chi1 is a finite order, and chi2 is pulled back from this Weil group of the base field. So we know then that the absolute value of tau of chi Z squared is equal to QMB times the rank of D0, where beta is the determinant weight. Just basically by this definition. But on the other hand, you know that Z acts by multiplication by lambda times rank of D0. So if you take this, you make these two equal, you will see that you get this equality here, that tau gamma squared is equal to QMB. This was precisely the theorem. Right, so to show that this then behaves well with respect to, let's say, this notion of determinant weights behave well with respect to maps of with respect to the exterior powers, you use this computational tool. So here's the proposition we want that it fulfills, that the determinant weights fulfills list item 3 of the desiderata. So this is the following proposition.
Wait, Magnus?
Yeah. Yes.
So the previous proposition was basically saying that if I have a geometrically irreducible least sheaf, then the determinant weight is the same as the weight? Or something?
Yeah. Yes. I mean, you need. It says the following. So if you have something that's you want geometrically reducible, and then you have that's less, and you're saying that it basically says that, I mean, it says that if you have some element in the center, you can sort of like compute the precisely what the determinant weight is by checking how this eigenvalues.
It's only relating the determinant weight to the center. We didn't relate it to the actual weight yet.
No, we haven't done that yet. It's just determinant. Yes.
Yeah, I thought this was like, yeah.
Yeah. No, it's just about how relating the action of the center to the determinant weights. That's all it is. But this is like a computational tool. So then what we want now is to prove that with this computational thing, we can prove that it behaves well with respect to tensors and with respect to the exterior powers. So here's the proposition, which shows that item 3 desiderata is fulfilled. So let F0 and G0 be list sheaves on X0 over K, and X0 is normal and geometrically irreducible. And F0 and G0 are any list sheaves. Now, 1 says that if F0, respectively G0, has a single determinant weight alpha, and G0 has a single determinant weight beta, then the tensor product F0 and G0 has single determinant weight alpha plus D. And here all weights are respect to this embedding of tau from QL bar into C. And 2 tells us that for gamma in R, we will let R gamma be the sum of the ranks of all irreducible constituents of F0, which has the tau determinant weight gamma. Then the determinant weights of the topic of the rth X0 power, F0, are precisely the numbers, the sum for over all gamma in R of n gamma gamma, where here this n gamma is some numbers here that sum to R. And here we can let n gamma be between 0 and the rank of this reducible constituent.
Sorry, can you say again, what is the definition of n gamma?
So n gamma is any number between 0 and R gamma, where R gamma is the sum of the ranks of all reducible constituents of F0. So basically what I want, you can think of it as follows. For every, I look at all irreducible constituents which have determinant weight gamma. And for each of them, I can, if I then look at what determinant weights are, I can choose here any n gamma can range from everywhere from 0 into R gamma. So I'm feeling I'm being a bit unclear, so please continue.
I think the question is like, well, there are several determinant weights. So you generate several numbers, and
yes,
any piece of like n gammas that satisfy the condition, you get one number, and this number is
precisely
one determinant weight. So you go over all options for n gamma that satisfy the condition.
Yes, that's precisely correct.
Okay, thanks. I was just confused about the quantifiers, but okay.
Yes, thanks. I think I was a bit unclear, so it was very helpful to ask the question.
N gamma are integers between 0 and R gamma?
Yes.
Okay.
Thanks. So here's a proof sketch on how you prove one. So replace their F0 and D0 by their semi-simplifications. And then you pick some element
What's
Z1
simplification?
So I take Jordan Holder series, and then I take just the I just replace these.
Graded.
Yes, precisely.
Yeah, so for other people, like you take the direct sum of the irreducible components of the associated.
Yes, that's precisely what I'm doing. So here's the sketch of how to prove one. So we replace F0 and G0 by their semi-simplifications. Then I pick some element Z1 in the center of their arithmetic monodromy group of here, and I pick some Z2 in the center of the geometric monodromy group of G0. Here it says F0, but should be G0. And I then take both the non-zero degree. Now I can apply this trick from above to see that precisely, well, the determinant weight, I can just act by Z1 and Z2 on this tensor product. Then you can see the determinant weight will be alpha plus beta. And you can show with a bit more care that 2 also follows from the same computation.
Magnus, I have a question. Maybe it's not important, and then we can defer to later, but there's this distinction between geometrically irreducible and just irreducible.
Yes.
And the first proposition is about geometrically irreducible, right?
Is it? I'm not sure, actually.
You said geometrically irreducible in the...
the scheme should be geometrically irreducible.
Okay. Not the sheaves. I see.
No, the schemes could be geometrically irreducible. So I think, let's see. Yeah, that's all I want.
Thanks. Okay,
yeah.
That makes sense.
F0 and G0 are general.
Yes, they're list sheaves, not necessarily.
Semi-simple.
No, just any list sheaves. So this will be like a very important computational tool in a short while. So let me just mention the item 3 of our desiderata. So if f0 and x0 is above, and I have a map from y0 into x0, and y0 is here a normal and irreducible scheme, and f0 is a map of k-schemes. If we then suppose that f0 has a dense image, then it turns out that, well, this should be the pullback of f0 and f0 here, this should not be g0, f0. They will then have the same determinant weight. So this is like we wanted to behave well with respect to maps. This is precisely that thing we have here. And the proof is in the same style as above. And you see that we have the condition that the map should be have dense image or be dominant. And this dominance is used to show that the image of the fundamental group of y has finite index in the fundamental group of pi 1 of x. This can be checked over a fiber at a generic point. So we need some condition for this to hold. Now that we have defined determinant weights, we want to prove our key theorem for today. First, let us recall that a scheme f, a sheaf f on a variety, or algebraic scheme really, x over k, is tau real if for all closed points x of x0, the characteristic polynomial of determinant of 1 minus the Frobenius of x, or the geometric Frobenius, times t acting on fx bar, and then we embed it by tau, if this has real coefficients. So a sheaf is tau real if this characteristic polynomial has real coefficients.
So this does not mean that the eigenvalues themselves are real, but only that, like, if you take all the symmetric polynomials, then they are real, right?
Yes.
Something like this.
Yes. That's precisely what it means, yes.
Okay, is that clear to everybody?
I'm not sure why it is dependent on tau. Can tau mix the real stuff with the complex stuff?
I mean, you basically asking if something is like, I mean, you want this, if this is true for all tau, then the coefficients are like totally real. That is, they're real with respect to every embedding. But you can have certain embeddings of some algebraic number which is not real, and some of the embeddings they're not necessarily real. Does that make sense to you?
This is what is confusing, but I think I
Like
can just take it.
If everything is like your over Q, your isomorphisms are over Q, they are abstract field isomorphisms, and as such, like R and C, they are like very, very.
Maybe I can just give an example. So every finite extension of Q, every automorphism of a finite extension of Q can be extended to an automorphism of C. So in particular, if you take the cube roots of, I don't know, 5, of 2, then you can permute them. One of them is real and the other one are complex, but you can take the real one to a complex one, and you can extend it to C, like to a very non-continuous automorphism of C.
My confusion was because of the fact that the real numbers don't have any, but this is exactly the point. Never mind.
Yes.
I was just confused.
Okay. So here's the theorem, what we want today. So let x0 over k be a scheme. Let f0 be a tau real sheaf on x0. Then the theorem is as follows. First is that f0 is tau mixed. And second is that if x0 is normal and irreducible and f0 is less, then the irreducible constituents of f0 tau pure. So this is a very powerful theorem, which will be fundamental, and it's not entirely obvious how to prove. So this is our goal now. We want to prove this theorem. So is the statement of the theorem clear to everyone?
So f0, like, it's a tau real sheaf, but it doesn't have to be Lis, right?
No.
So it's a general constructible QL bar sheaf.
Yes.
Which is real. Okay.
Yes.
Tau real.
Right.
Isn't one conflicts with two?
Why?
Can something be both tau mixed and tau pure?
Sure. I mean,
Okay. Tau mixed is finitely many. Okay, sorry. Yeah.
Yes. No worries.
Finitely many.
So this is like the ascended key theorem. So we'll prove this theorem in a while. So first we'll note the following. If f0 is tau real, then I can take the logarithmic derivative of this characteristic polynomial. And this logarithmic derivative is precisely the sum from n equal to 1 to infinity of the tau applied to the traces of fx, and then this is the kth power, and this is the times n. And then I take times tn minus 1.
And Magnus, can I ask? I'm sorry.
No worries.
Can you remind me what is tau mixed?
So tau mixed is that you can find some filtration of your sheaf such that the quotients are pure.
Ah, okay.
So I think it's like what happens if you close
Finite.
tau pure
Finite,
under
precisely,
extensions, right? It's what happens if you close tau pure under extensions.
Yes. That's precisely
Okay,
what
thank you.
Yeah. So as I said, if I have a tau real sheaf f, I can take the logarithmic derivative of this characteristic polynomial, and I get the following series. And you note then that if k is even, then the coefficients of this here will be positive. So, because, I mean, if the coefficients of this logarithmic derivative is positive, then clearly the coefficients of this guy here is also positive because it's just e, then I integrate over pt. And we will use this positivity of coefficients to prove the theorem above. But before we do this, we will spend some time on how Deligne got the inspiration for his argument of doing this. So this is a hard thing, and I think, and Deligne got the inspiration how to prove this by looking at a paper of Langland's, and where he showed how to deduce the Ramanujan conjecture for certain automorphic representations from analyticity of L functions. So this might be some big words that might scare you, or maybe it doesn't scare you, but I'll try to make it understandable. And I think it might be good to just see where these ideas come from, and then let's see how Deligne applied them to this theorem above. So, as I said, Deligne read the argument of Langland's on the Ramanujan conjecture and realized that in the geometric setting that is for schemes over finite fields, you can adapt Langland's argument to deduce the theorem above. So now I will speak about the Ramanujan conjecture, automorphic representations, and Rankin's trick. So if you're not familiar with modular forms, don't worry, you don't need to be. Everything here will be more or less treated as a black box. So let us recall the Ramanujan's tau function, which is defined from the natural numbers into Z. This is defined by the following inequality. So I take the sum of tau n qn, and I let this be equal to q, the product of n from 1 into infinity, of 1 minus qn to the power 24. And here we let q is equal to e 2 pi I z, and the imaginary part is greater than 1. So this infinite product here determines tau n. So this is then the coefficients of this power series here are precisely the series here is precisely the Ramanujan tau function. And now you can show that delta here, this function here, which I define by this infinite product, is a modular form. It's in fact a cusp form of weight 12 and level 1. And Ramanujan conjectured that that tau n, the absolute value of tau n, is less than or equal to dn times n to the power of 11 over 2. And here dn is the sum of the divisors of n. And Ramanujan managed to prove that tau n is equal to O n to the power of 7 in 1916. And then Hardy and Littlewood proved that tau n is equal to O to the power of O n to the power of 6. And then Rankin proved that tau n is equal to O n to 29/5 plus epsilon for all epsilon greater than 1. This was proved in 1939. And then with the Weil conjectures, Deligne proved the Ramanujan conjectures as a consequence of them.
Magnus, is
Yes?
this 11, is it like 12 minus 1 or something? Like how, what's the 11 has to do with the situation? Is there like some...
Oh, I see what you're saying. So you're meaning, so the question why, like how it like comes up in this situation? What's the...
Yeah.
So let me, 1 second, let me think of it. I mean, yeah.
Yeah, 11 is 12 minus 1. In this case, it's the n to the power 6 is an easy Fourier transform computation. It's a direct estimate on the coefficients, and then the whole difficulty is winning this 1/2. And that's where Deligne comes in, because these coefficients are actually eigenvalues of Hecke operators, and the Hecke operators mod p are the Frobenius and Verschiebung, which is sort of like the dual.
The inverse Frobenius, yeah.
Yeah, inverse Frobenius. So that's how this is related to this whole business.
Thanks.
Yeah. So you can also then generalize Ramanujan conjecture to automorphic representations. So, as I said, you don't need to know what automorphic representations are. You will just define what we will need about them for this to make sense. But for simplicity, if you know something about this, I will let G be equal to GL2. And I will now let A be the adels of Q. And let chi be a Dirichlet character. Then a cuspidal automorphic representation, pi V, of the G AQ. So this is the adelic points of GL2 with central character chi. It will for us be just a black box. And we will assume that the representation is unramified for also simplicity. So instead of defining precisely what a cuspidal automorphic representation is, we will list the properties that are useful to us to understand Langland's argument. First, how to think about this is that a cuspidal automorphic representation, pi v, is like some sort of, not quite representation, but almost representation of GL2 AQ on the complex vector space V, and it will satisfy certain technical conditions. Second is that every representation, pi v, can be factored as a tensor product or a restricted tensor product of pi v, where V now ranges over all places of Q. And pi V is some sort of representation of GL2 Q. And third is then that when pi is unramified, which we assume, that then any of these local representations will be parameterized by a semi-simple conjugacy class in GL2C. And this conjugacy class will be of the form alpha V and beta V. These are called like the Satake parameters, I think.
What do you mean by is parameterized?
So I don't want to go, so there's a bijection between the local representations and these semi-simple conjugacy classes.
Okay, thanks.
No worries. And then 4 is that each new form, which is a certain type of holomorphic form satisfying certain transformation properties, it will give an automorphic cusp form for this with central character chi. And the 5th is the most important part for us, that whenever we have a representation pi of, and we write this a direct product as a tensor product of this pi v, we assume that pi is unramified. And we have representation of GL2C into GLW, where V is some complex vector space. We can then define something we call local L factors associated to the representation pi V and the representation here, E. The local L factors are defined as the characteristic or the determinant of the identity minus P CV, where here CVs are conjugacy clause as above, times V, the absolute value of V to minus S minus 1. This is for if V is a finite place. And we have a similar description if V is in the infinite place. You can count the gamma function. So before I go through is
what do you mean by the absolute value of V? Like is V is a place, right?
V is a place, so I mean it doesn't really do anything in this situation.
Okay.
I'm just writing it for some, it's more important when you have general number fields, but in this situation it doesn't matter.
Okay.
So is these 5 properties somewhat clear? I want you to really, the thing to really recall is maybe 3 and 5 is the most important thing. Then namely with that, when pi is an unramified cuspidal or automorphic representation, the local factors are parameterized by the semi-simple conjugacy classes, which are given by 2 complex numbers here. And lastly, that when we have such representation, I can define this local L factor. So this is what will be important for us.
But what is this local L factor? Like,
what it is?
Yes, like, is it?
It's precisely this, given by this function here is the local L factor.
Function on what?
So I have a real parameter. This would be a complex number S.
Ah, okay.
Yes. So it's sort of like defining something that looks very similar to our L functions from above.
Okay, so this this absolute value of V is a number, some number, which is okay. Cool. Mm-hmm.
This is the. So now the generalized Ramanujan conjecture for pi V is then that for V finite, we have that the absolute value of alpha V and beta V should be equal to 1. Just you recall, these are the Satake parameters associated to the automorphic representation. And for the infinite place, it's the statement that the real parts of alpha V and beta V are 0. And with some work using 4 here, you can show that this implies the Ramanujan conjecture described above. And now what Langlands did was they showed that if you had a very good control of this L function here, which is, I will define the L function L S pi P, near P is some representation of GL2C into some vector space GLW. If you knew that this L function was analytic for real part greater than 1, for all representations P, then the Ramanujan conjecture for the automorphic cusp representation holds. So he deduced this as follows. So here's the proposition by Langlands. So if LS pi P is analytic for all S with real part greater than 1, and for all representations P of GL2C, then the Ramanujan conjecture for pi comma V is true. This is the. So I also want to make clear, do you have a somewhat grasp of the objects that are floating around here? Is this L function I defined, is it clear at least what it is in some sense?
Not really. It's kind of hard to follow all the definitions.
Right. So is there something in particular, Shai, that's confusing you?
So, for example, what does the P do there? Like, what's...
Okay, perfect. Thank you for telling me. So P is some representation of GL2C in the GLW. You're with me on this, right?
Yeah.
And then given such a representation, I can define a local L factor. This is like some complex function that depends on this local representation here and our representation P. It's precisely the determinant of the identity minus the Key CW, where I apply the representation to this element here. So I get something that lives in GLW.
So the CV comes from the pi at one of the
Yes,
places,
pi.
and
Yes,
the
the
P
CV
is like applied to this matrix.
Yes.
Okay.
So this is how you define the local L factor. So then what I do is that I take the product of these local L factors, and this gives me precisely this L function. Is things a bit more clear now, Shai, or do you want to? I want people to understand, so please interrupt me so this is clear.
So the product is over all of them, right? Not just
the product is
random
over all places, yes. It's over all primes in the infinite place.
So the analyticity condition, is it?
Yes.
I mean, are the local factors? Local factors are analytic, or like what is the state? Is it a statement about like poles or something, or is it a statement about being holomorphic? Like what is the statement? What is the condition?
So I'm not sure I understand you. So what I want is that this product should be analytic for the all S-grade, all real numbers, all imaginary, all complex numbers with real part greater than 1.
I think Lior is asking, like, do we know anything like this for any of the local factors separately, or like this is a condition which really factors? Like, is it true that each one of those is analytic and we are worried that the product might not be, or that we don't even know, and that, or that maybe we require that each one of those is analytic?
I see. It's a good question, and I don't know a good answer. So if someone knows a good answer to this, I'm very happy. But I don't know a good answer. Yeah?
I think that, I mean, pretty much like every local factor is, I mean, it's like very simple function, right? Like.
Oh, right. Yes, you're right. Yes. Yes.
Just think about right. Like, I mean, it's almost like.
It's almost like, yeah.
If P is like maybe the trivial representation from GL2C to GL2C.
Yes.
I mean, I'm not sure what W is here, but I missed a bit, but. I mean, then this would be something like the L function of a modular form. And then I think that like you should think about this P as being like maybe taking all the symmetric powers of GL2C or something like this, like all the symmetric powers representations. And this like analyticity is something you always maybe have for like some real S larger than something.
Yes.
Like the important bit is that it's literally larger for 1 for all of them.
Yes.
So
okay, so
like
it's a question about poles.
It's a question about convergence. It's not a question about like being defined but not analytic or something like this.
Yeah, so I think the point is that it converges like not like for every P, it converges like at this amount, like from the same like half plane. This gives you like the control on the kind of how these like local L factors grow that is related to like how, like what's the size of the eigenvalues.
Yes.
But I think that in our situation, we assume that the L function is analytic and we want to show that the alpha V and beta V satisfy something.
Yes.
Yes.
And
we're just trying to understand what the analyticity
means
is about. So it's about like the convergence of this product of functions.
Yes.
No, but like maybe like it would be not so hard to show that like this is.
But you want to convert this for specific S
larger than something.
You want real.
The important is that for the same one.
You want for real greater than 1. Yeah.
Yes. Okay.
So then what left?
The idea is that if you have some control, then this ranking trick of going to tensor powers allows you to tighten it, but you need some initial control.
Yes.
That's basically like you described at the beginning of your talk. If you had
this tensor power trick,
specific C, and then you can do that.
Yes. All right. So hopefully these objects are now a bit more clear. So here's the proposition of Langlands, which denoted that if you had this analyticity for this L function for all representations P of GL2C, then the Ramanujan conjecture for this automorphic cusp form is true. So here's the proof. So you first let sigma be the standard representation of GL2 on C2. Let sigma bar be the conjugate representation, and you form P, which is the sigma tensor sigma bar. Then you know that the trace of this new representation is precisely the trace of the standard representation times the trace of the conjugate representation. This is precisely the trace of sigma k CV to the second power for all E. So then if you look at the logarithm of this L function, you get precisely the following. So you get a product over all V, a sum over all V, and where V is the places. And then for each V, you have the sum from k equal to 1 to infinity of the trace of the absolute value of the trace of sigma k CV squared divided by VKS, where S is your parameter here and K is. Then you note that this has positive coefficients, so then the Dirichlet series defining this logarithm, this L function also has positive coefficients.
The way you use sigma is like the special thing is that P is the tensor product of representation and its conjugate, right? And therefore.
Yes, precisely. Yes. So therefore, this has positive coefficients. So therefore, the Dirichlet series for this also has positive coefficients. And then you can use Landau's theorem, which tells you that this the Dirichlet series for this L function converge absolutely, and you know also that the logarithm does. So this implies in particular that this PCV here has eigenvalues all less than or equal to V in absolute value, because otherwise this will not have absolute convergence. But you know also that the eigenvalues of PCV here are precisely the AV squared and BV squared. So when you then take roots, you get that AV is less than or equal to V 1 over 2, and BV is less than or equal to the square root of V. You can now employ the same trick to the tensor product, tensor powers of your representation. Then you conclude that AV is less than or equal to the 2mth roots of V, and BV is equal to the less than or equal to the 2mth roots of V. Then you let m go to infinity, and then you sort of get this inequality that AV is less than or equal to 1, and BV is less than or equal to 1. Then you can use a dual representation to conclude that AV and BV are equal to 1 for all finite V. And you can apply a similar trick to the infinite places. So the important thing is really is that you somehow use positivity conditions. So you use representations to create use this standard representation, then you take the conjugate representation. So then you get a L function such that the Dirichlet series has positive coefficients. And then you note that this positivity forces the eigenvalues of the representations to be less than or equal to V in absolute value. And then you analyze what the eigenvalues are, and then you can show this inequality, and you apply the same trick to the tensor powers. So this is what I think Delin read, and what he then used as an inspiration for the theorem we talked about above. Right. So as I said, I think Delin read Langland's argument. Then he went to Rankin's paper on this Ramanujan conjecture that I spoke about previously, and then he realized that you can use some similar argument in the geometric world. So this is what we will use now. We will use some positivity or coefficients together with some tensor product of representations to sort of try to control. So here's what we want to prove.
Magnus, do you maybe want to take like a 5 minutes break? And
yes, absolutely.
Also, like everyone can rest and ask questions in the meantime if they have any.
Yeah.
I will keep the recording on so that people can hear the questions. So in 5 minutes.
Yes, perfect.
So Magnus?
Yes.
But you said that this is actually not just an analogy, but he actually proved somehow the number theoretic case
Yes,
from
Deline proved this. Deline proved the original Ramanujan conjecture that I spoke about above here. That the this part here, that if you have a modular form, that you have this inequality. And he proved a more general theorem actually that says that he proved a general theorem about some about inequalities of these coefficients of certain cusp forms. But this conjecture, this generalized Ramanujan conjecture is much more general, and Deline did not prove all of that. He just proved the holomorphic part.
Yeah. What you need is to show that this thing can sort of be, to use Deline's theorem, you have to show that these kind of representations are actually representations of Frobenius acting on some piece of cohomology.
Yes, I mean you take, yeah.
And here the weight is 12 for the delta function, and you know for weight 2 that it's that it's part of the cohomology of the modular form. So here you had to look at more complicated varieties, Kuga-Sato varieties, and embed this particular thing as part of their cohomology, and then use his theorem, and that's how this is proved.
Yeah, I mean, if I recall correctly, I mean, for this modular form thing, I think you like use the universal family of elliptic curves over the modular curve, right? And then you push forward the local system QO bar, and you look at the.
Well, you have to take powers of the.
Yeah, I mean, you take the symmetric powers of this.
Yeah.
This push forward. Then you look at the. Yeah.
Yeah, that's the Kuga-Sato thing. Yeah.
Yeah, right.
Yeah, and this is actually how also Sato-Tate is proved, more complicated, but
right.
Yeah. Yeah, maybe one more remark. Actually, all L functions of algebraic varieties are supposed to come from automorphic forms, and that's the only way you will be able to, or at least up to now. Maybe now I think maybe there's one or two other examples, but essentially that's the only way to prove the analytic continuation and the functional equation for L functions.
Yes. So what are the other examples that you're talking about?
Comes from the theta function. And Weil's, what he proved was that it comes for elliptic curves, and that's why actually the Burt-Swinnerton-Dyer thing is actually defined. Otherwise, if you don't have analytic continuation, you can't even define the L function at the critical point.
So I mean, you said that you have now we may have two other examples. I mean, of how we can.
I think that there was there is this work with 10 authors with Scholze and.
Oh yes, I see what you. Yeah, the 10.
I think that's the only thing, and actually, yeah, and Min-Young Kim with this. Chern-Simons, which I understand you're working on, that's supposed to be another venue for.
Yeah, we'll say we're far away from anything like that at the moment.
Yeah.
So yeah.
I think you can start if you want.
Right. Okay. So now that we have at least we've at least seen what Langland's argument is, but maybe we did not understand it fully, but we have at least seen it. We will try to see how this was adapted by Deligne. So recall that what we wanted to prove was that if x0 is over k, and f0 is a sheaf on x0, which is tau real, then we want to prove that f0 is tau mixed, and further that if x0 is irreducible normal and d0 is Lis, then the irreducible constituents are tau pure. And as usual, you can reduce the statement to curves by Bertini arguments. So we will start by proving a version of this for curves. And then we will like slice by curves the situation, as you always do in this business. So here's the statement about here. So, right. So here's the lemma we'll first use. So let F0 be a Lis sheaf on a geometrically irreducible normal scheme x0 over k. Then if F0 is tau real, then all irreducible constituents are tau pure. I just want to see if I, 1 second. Yeah, I want this to be, F0 should be a curve here. I mean, x0 should be a curve. So the lemma should be that I'm working over, we have a Lis sheaves on a geometrically reducible normal curve x0 over k. Then the statement is if f0 is tau real, then all irreducible constituents are tau pure. So you should read normal curve here scheme. So that's what we will prove. If I have a Lis sheaf on a geometrically reducible normal curve x0 over k, then if f0 is tau real, then all irreducible constituents are tau pure. This is like the curve situations of this statement here. So here's how we will proceed by proving this. First, we will start by bounding the eigenvalues of the Frobenius for the closed points of x and some x bars and geometric point over x. We will then prove more precisely the inequality that tau alpha is less than or equal to, tau alpha squared is less than or equal to nx to the power of beta, where beta is the largest determinant weight of f0. And here, alpha is an eigenvalue of the Frobenius here, and n of x is the size of the residue field at the point x. So to recapitulate, our plan is first to bound the eigenvalues of the Frobenius at the point x. We will prove the inequality that for any eigenvalue of the Frobenius, the absolute value of tau alpha squared is less than or equal to n of x beta. Beta is the largest determinant weight, and n of x is the size of the residue field. So this is what we will start by proving. We will then replace f0 with a simplification, and then we will apply this inequality here to exterior powers to conclude that the constituents are tau pure. So this is the plan how we will prove this statement here. Let us go ahead with this plan. So to prove 1 here, you see that this is a statement about certain points here. So we can assume that without loss of generality, that f0 is non-zero and that x0 is affine. Then with beta as above, the largest determinant weight of f0 with respect to tau, we have then that by this argument here previously about how determinant weights behave in the tensors, that R beta will be the largest determinant weight of f0, the R tensor product of f0. You can then consider the L function here, which is the product over all points in x of the characteristic polynomial of the Frobenius and then t dx. And then we apply this to, when we take the Frobenius on the 2kth tensor power of f0. And by Grothendieck-Lefschetz trace formula, this is precisely the determinant of 1 minus ft acting on the first compactly supported cohomology of x with coefficients in the 2kth tensor product of f, divided by the same thing, but we just the action on the second cohomology. So before I go through, I want to ask, is the statement, what I've said so far, clear? I want to prove a certain inequality, and I assume that x0 is affine and that f0 is not equal to 0.
Can you remind for a second what's the statement we are first proving right now? That over a curve, f0 is a Taurian sheaf, and the first statement is that we bound the eigenvalues by beta. Okay.
Yes, we bound the eigenvalues by
this. That's the largest determinant weight. Yeah.
Yes, this is what we want to do. We want to bound the eigenvalues with this determinant weight here. And we do this by sort of like taking the 2k tensor power of this or sheaf f, then we form this L function here, and we then use the Grothendieck-Lefschetz trace formula to conclude that it's precisely a quotient of these two different functions here. The determinant of 1 minus ft acting on the first compactly supported cohomology, and the same but acting on the second compactly supported cohomology. And note that, yeah?
Yeah, it says here that H0 with compact support vanishes.
Yes, because I find.
Can you? I guess it's simple, but I don't see it.
Well, would not say it's simple. I mean, but it's. There's
f0 is not only constructible; it will be like really constant here. Right?
Yes.
That's like so a
constant
section
or
will.
Smooth.
What?
F0 is least, right?
Yes.
Smooth.
Yes,
a smooth sheaf, there was a statement that was supposed to be proven at some lecture, but it was somehow missed, that if you have a smooth sheaf on an affine scheme, then its compactly supported cohomology vanishes.
Yes.
This is a statement that was somehow fumbled, but it was used earlier, and we need it now, and we will need it later. So
I mean,
okay.
Yeah. Okay.
So why doesn't the other compactly supported, like what, the zeroth, only the zeroth vanishes?
Yes.
Okay.
It's like
because something is locally constant. So if it's something locally constant, like intuitively, if something locally constant, and you have a compactly supported sections on an affine thing, then it extends everywhere the section because it's locally constant. So everything is compact, but compact and affine is like finite. So
this is actually a proof.
Yeah. Right. So now the idea is to follow Langlands. So in the above the left-hand side here, we play the role of the L function or the automorphic form. Now you can use an easy application of Poincare duality to note that the zeros of this tau determinant 1 minus ft and acting on h2c x f to the 2kth tensor power, the zeros will satisfy that they're all greater than or equal to q to the minus 2k beta plus 2 over 2 power. So this is just basically, you just use Poincare duality. It's not hard, but I will not go into it. Because this is like, yeah. So then you know, since the zeros are greater, they satisfy that they're greater than or equal to q minus 2k beta plus 2 over 2. You know that the left-hand side converges.
Can you repeat what you said before? You're saying that's by application of Poincare duality? What?
Yes, by application of Poincare duality, you can look what you can see what the zeros of this characteristic polynomial is. And you can show then that the zeros satisfy that they're larger in absolute value than q to minus 2k beta plus 2 over 2. Because by Poincare duality, you can identify this with h0 x f tensor 2k, but it would take twist. And then you can quite easily analyze what the zeros will be.
Oh, okay.
Yes, that's the statement.
Actually, this
so
was
how does beta comes into it?
This,
maybe that's what I don't understand.
What's these? Yeah.
We actually had discussed this yesterday because this was in an affine set. The number of points cannot be greater than q to the dimension of the affine.
Yes.
That's essentially what's.
But my question is, how does beta get into it? Like how?
I don't understand fully the question. So what's the?
You're saying that T0 is like at least q to the minus 2k beta plus 2 over 2. My question is, how does beta, like the determinantal weight, gets into like?
How it gets into the picture?
Yes.
Right. So 1 second. Let me think about it. 1 second.
I mean, you can continue and maybe I'll ask in the end.
Yeah, let me continue. I think I can explain, but let us. I think I can explain this, but let's postpone it for. Yeah. Then you can see that the product of the left-hand side will converge for tau less than or equal to q minus 2k beta plus divided by 2, because, well, you see this is precisely the poles of this guy. Now, since you know that each factor in this left-hand side will have non-negative coefficients, and it will also have leading coefficient 1, they will converge for the same values of t. This is just some statement about analyticity of infinite products. So this implies that each individual L factor here will have no zeros for t less than or equal to q minus 2k beta plus 2 over 2, because then this will have some poles. But now if alpha is an eigenvalue of the geometric Frobenius, then you know that alpha 2k is an eigenvalue of the Frobenius of this 2k tensor product. So this implies that the absolute value of tau alpha 2k is less than or equal to q dx, where dx is the degree of the residue extension of 2k beta plus 2 over 2.
Magnus?
Yes?
I'm actually also confused by the question of Elad. So beta is our determinant weight, right?
Beta is our determinant weight, yes.
And we haven't yet related the determinant weights to the actual weights.
No, that's not somebody. Oh, I see what you're saying. So.
And the first inequality seems like it's obviously hold for the inequality you wrote for the eigenvalues, for the roots. It like obviously holds if you replace beta with the weight, but with the maximum weight, but then it's not clear to me how to parse the statement.
Let me think. So can you repeat the question?
So if you replace beta in this inequality with T0, if you replace beta with the maximal weight of F, then this is it's very clear to me now.
Yes.
But then if you replace it with beta, it's not clear to me why this inequality holds. Because it seems...
Can I come back to that later on?
Yes, for sure. I just wanted to reiterate that this is like a point that also confuses me.
Yes, I think I can explain, but I will want to come back to it a bit later if that's fine.
Yeah, it's a good idea. It's a good idea.
Yes.
Let's continue.
Yeah. Right. So given that this somewhat mysterious inequality holds, then we can conclude that these L factors here have no zeros for t less than or equal to q minus 2k beta plus 2 over 2. But we also know that if we have alpha an eigenvalue of f of x, then alpha 2k is an eigenvalue of the Frobenius on the 2k tensor power. So we know also what the zeros of this guy here is, because, well, it's characteristic polynomial. So this implies then that tau alpha to the 2k power is less than or equal to q dx 2k beta plus 2 over 2. This is just because, well, when we try to find what the zeros of this guy here is, we know that, what is it, the tau alpha 2k over d of x is 0 of this, so we'll multiply it by d of x, and then we'll get this inequality. Then I could take 2kth roots of this inequality here. I will let then k go to infinity, and then I get the inequality that tau alpha is less than or equal to q d of x beta. This is precisely n of x of the beta. So we employ this tensor power trick that I talked about previously. So this is just analysis, but you see, what we're really doing is that we're having some control of the poles of this L function. And we apply this control to somehow know something about the zeros of this. We know that the zeros of this L factor here is precisely something related to the eigenvalues. And then since we have such good control, so then we get some inequality that looks as the tau alpha 2k is less than or equal to q d of x 2k beta plus 2 over 2. Then we can just divide by 2, take the 2k roots and the k go to infinity. So this is like clearly inspired by Langlands.
Magnus?
Yes?
So, but I missed, where did you use this assumption that that it's, I forgot what the name is, totally real, or?
Oh, the real thing was used because you see, here, we said that here, each factor in the left-hand side has non-negative coefficients and leading so this is where we use this, that the left-hand side non-negative coefficients, because you see what I talked about for a few slides previously. I said something around here, I think, yes. That you see that the logarithmic derivative, if I have a tau real thing here, if I take the 2kth power, then the logarithmic derivative will have positive coefficients. So this implies also that this characteristic polynomial here, tau det determinant of 1 minus fxt, that this also has positive coefficients. So this is what's used. Here's what the real thing is used. It's used to deduce a positivity statement on the coefficients of these local L factors. Does that help?
Yes, but so.
Yeah.
But in any case, it seems like you're just using this particular tau, right?
Yes, I'm using this particular tau. So this is just a statement about this particular tau. If I knew that it's real for all tau, then I would have this. Then I would have this inequality for all tau.
Yeah.
Yes. So you see, this positivity thing really comes in to show that the coefficients are positive. That's where it's used. So now what we want to prove is that we want to prove that it will replace F0 with a semi-simplification. And when we apply star cleverly to exterior powers, we can conclude the constituents are tau pure. And in interest of time, maybe I will try to be a bit brief about this point. If no one else, if you want more detail, I can stop you. You can stop me. So you take, yeah. So here's the question. Do you want the proof of 2 or do you want me to go ahead?
I think it's hard for us to prioritize, but if you need like extra 5 minutes or something like that, you can definitely steal 5 minutes from the break.
Okay, so let me try to then go through with 2 then. So recall that we want to prove that we want to apply this inequality here, that tau alpha squared is less than or equal to mx beta. We want to apply this inequality so that when we replace F0 with semi-simplification, we want to conclude the constituents are tau pure. So this is what we now try to do. So as I said, we can now assume without loss of generality that F0 is semi-simple and that F0 is non-zero. And now we will order the determinant weights as gamma 1 less than gamma 2 and so on to gamma r. So we have R determinant weights, and we will let F0i will be the direct summand of all constituents of determinant weight gamma I. And we will let Ri be the rank of F0i. So I will now let alpha to the power of j, I. This will, in my notation now, be an eigenvalue of the Frobenius acting at the point x, acting on the jth direct summand, acting on f of 0j. So this will be the notation of an eigenvalue on f0j. And we will now prove that for this, any eigenvalue, we will have tau alpha j I is less than or equal to n of x gamma j.
So just to recap, like the gamma I is like satisfies that the product of the alpha I j over j is q to the power gamma I or something like this, right? Did I freeze or did Magnus freeze?
No, I think Magnus got disconnected.
Yes.
Yep.
Yeah.
Oh no.
Does anyone know the answer to my question? Like, is it true?
Can you say it again?
What was the question?
If I just wanted to make sure that I understand, so the gamma I is related to the alphas, like the eigenvalues, by the fact that if you take the product of all of the eigenvalues over j, like alpha ij over j, that this is the determinant, so it should be q to the gamma I or something like this.
To the two.
I think you switch I and J, but yes.
Okay, yeah.
But
Something of this.
Like you said,
like
that
the
alpha
normalization
with
of
J up is like the thing on Fj.
It was
Does anyone have Magnus notes?
No, I think he didn't upload them.
Can you hear me?
Yes.
Yeah, and I also heard that you said that I forgot the R that comes from the normalization of the rank. Yes.
Now, if you want, the determinant weight is the average of the weight. It's the average. It's the geometric average of the weights.
Ah, that's a good way to say it. Thanks.
Well, it's the average because the weights are logarithmic.
Okay, I'm talking with Magnus. He's trying to reconnect, and hopefully it will be soon.
So maybe in the meanwhile, someone, maybe Tomer, can just like give a like recap of where we are, what we're trying to prove, what's going on.
So the main result that that Magnus is talking about, right, is the relationship between being tau real and tau mixed. So let's recall what is the statement. The first thing is that if we have a smooth sheaf, which is and it's tau real, then all the irreducible components are tau cube. Okay, that's the state.
I thought this was true even if you're not assuming you're smooth. Oh, Magnus back.
Yeah, I'm back now. Great. So yeah, I got some problem with my internet connection.
Yeah. Okay. Magnus, should I let you? Yeah.
Yes. Let me just share my screen. So someone allow me to share my screen?
I think everyone is allowed to share their screen. Do you have a problem with that? Like, does that not work?
Now, perfect. Now, great. Can you see my screen?
Yes.
Yes.
Okay, so let me just run 2. So
can you close the thing on the right?
Yes. Thanks. Now I'll close this one. Yeah. All right. So we had ordered the determinant weights by size, and we had let this F0I here be the direct summand of all the constituents that had determinant weight gamma I. We had Ri as the rank of F0I. Then I had let alpha ji be an eigenvalue of the Frobenius acting on the j's summand here. And the statement is now that it will prove that tau alpha ji is less than or equal to n of x gamma j. I can then apply the same argument to the dual to conclude that we have an inequality. This means precisely that F0j is tau pure of Voigt gamma j. And now to do this, we do this, use this compatibility, but with determinant weights and wedge products. So for any n with between 0 and less than or equal to r, where r is the number of determinant weights, we'll let n be equal to the sum from 1 to n of Ri, where Ri is the rank of the ith direct summand. Then the n plus 1th exterior power will look something like, of f0, will look something like f0 n plus 1 tensor this determinant of f0y from I to 1 to n. And then some other direct sum which we don't care about. And then from a previous lemma, we can see this has largest determinant weight gamma n plus 1 plus the sum from I from 1 to n of Ri gamma I. Now, you can then see that the Frobenius acting on this exterior power here will have the eigenvalue alpha I n plus 1, then product from k from 1 to n, the product from j from 1 to the r of k, of alpha j of k. And here this alpha 1 k to alpha r k. Okay. This is precisely the eigenvalues of the Frobenius acting on the kth component of this. But we have now just proved previously that we have the inequality that tau alpha I n plus 1 times this direct product is precisely less than or equal to n of x of the top of the maximal determinant weight. This is precisely what it is. But now you can see that the definition of determinant weight precisely implies that this product here is just the sum from 1 to n of rk gamma k. So we can just divide out by this factor here. And this gives us that tau alpha I n plus 1 is less than or equal to n of x gamma n plus 1. And this says that we're done. So we have thus proved the second part here, which was that for if we replace f by semi-simplification, then we conclude that the constituents are tau pure. So to conclude, we have proved the lemma 1 here. So f is a list sheaf on a geometrically irreducible normal curve. Then if f0 is tau real, then all irreducible constituents are tau pure. This is what we have now proved. And what we now want is to prove the general theorem. So this is what we want to prove now. So x0 is a scheme of finite type over k, and f0 is a sheaf on x0, which is tau real. Then we want to show that f0 is tau mixed. And we also want to prove that if x0 is irreducible normal and f0 is less, then all the irreducible constituents are tau pure. So,
Magnus, we can hear you.
You can hear me. Okay,
Yeah.
Sounds okay. Good.
I can hear you.
Everyone can hear both.
Yeah,
everything is good.
Everything is cool.
So there was disconnected, but yeah, great. Can you hear me now?
Yes.
Yeah.
Yeah.
Perfect. Okay. Yeah. So is the statement of this theorem clear to everyone?
I think this was the one from the this is the
Yes,
main one.
This is the main theorem, yes. So this is what we now want to prove finally.
We proved it for curves so far.
Yes, we did this precisely for curves. Now we want to prove the general case. So now I want to say that 2 will be a direct consequence of 1, because when we have on a normal and an irreducible scheme, when we have an irreducible list sheaf f0, which is tau mixed, it will be tau pure. This is a theorem from before. I will not prove, but it was mentioned. I think it's mentioned as a consequence of the semi-continuity that Ariel proved. So we will just prove 1 here. So that if we have F0 sheaf on X0, which is tau real, then it's tau mixed. And the proof in Kiel-Weissauer's book is somewhat ugly. So here's another way to prove this. So you can first reduce to X0, which is normal and irreducible, by taking normalization and consider the connected components separately. This is what we'll do. We'll assume that X0 is normal and irreducible. It's a quick step we can do. You can then reduce to when F0 is irreducible, and then by twisting by a Weil sheaf that is pulled back from the base field, you can assume that F0 is also an honest sheaf, not a Weil sheaf. You then want to prove that F0 is tau pure of weight that is of course equal to the determinant weight. So to recapitulate, we will want now to prove just that F0 is tau pure of weight equal to the determinant weight, and F0 is now irreducible and an honest. So here's one way to do this. For any closed point in X0, find a smooth irreducible curve from C0 mapping into X0 such that the pullback of your sheaf here is irreducible, and that this X should be in the image of phi. This is a statement. So if you can find a curve that's smooth and irreducible, C0 mapping into X0, such that when you pull back F0 by phi, then it's still irreducible. Then I claim that the theorem then holds. Well, because what we have shown just now is that then the pullback will be tau pure of weight that's equal to the determinant weight of the pullback. That's equal to the determinant weight of F0. So this means that Fx acting on this stalk here is eigenvalues of weight equal to the determinant weight of F0. So this holds for all x equal to X0, so the theorem follows. So really what we're, as I said, you can just reduce to the case of curves by pulling back along this nice curve, and then you note that the pullback will be tau pure of weight equal to the determinant weight of the pullback. This is the same as the determinant weight of your original sheaf. And this just means that the Frobenius has eigenvalues equal to the determinant weight. So it's pure. So I think this is a less complicated way of proving it. Of course, you might then ask, well, why does curves like this exist? This will be a black box for our talk, but you can prove the following, which is not extremely hard. There's a theorem by Hélène Hainaut and Moritz Kurtz, is that you can find curves as I specify in 3 here. So the purity theorem holds because we're just reducing to the case of curves. So is the proof of this clear, people?
Wait, can't you find, if you have a normal variety, then at any point there's a smooth curve through it, isn't it the case?
Sure, but
the problem is that the pullback would be reducible.
Yes.
Ah, you want the pullback also to be reducible.
Yes, precisely.
I see. So it depends on the sheaf.
Yes.
Okay.
So this is what I want. I need a particular curve that the pullback is irreducible, and then I can apply our previous theorem.
It's reasonable because you want like to have like enough loops in order to the representation to be reducible. So
yes,
you have Burnside, so you just need like finitely many like curves. So it's like elements in the pi one. So it's not really a big deal, I think.
No. Right. So this proves the purity theorem. And before I end, I want to say that we have the following conjecture of Deligne, which is stated in Weil 2, and I believe it's now proven by Vincent Lafort, but I'm not 100% sure. So what Deligne conjectured and Vincent Lafort proved was that whenever we have a scheme of finite type, or an x0 over k, then Deligne conjectured that every Weil sheaf is mixed. And I think this is now clear. And I think this is a very nice theorem. I think it's so where this field has sort of progressed since the Lean's original. All right, I think I'll stop there. So please ask me questions. We can try to discuss it. And anything, yeah. So thanks for listening. Sorry for the.
You mean every smooth Weil sheaf?
I mean every Weil sheaf actually.
Every Weil sheaf.
Yes.
Wow. Okay. No, like constructible Weil sheaf.
Yes. Yes.
Okay. Yeah.
Okay, so thanks, Magnus.
Sorry for the internet problems. It was, yeah.
No problem.